Neutrinos are some of the most mysterious particles in the universe, with only dark matter baffling scientists as a more mysterious phenomenon. While there are neutrino detectors on the lookout for the rare particles, we may need to look to the massive scales of the Pacific Ocean to find a class of ultra-powerful neutrinos. And with a small-scale demonstration in the works, scientists may soon find out if this concept will work and transform our understanding of the universe. Neutrinos are produced in large quantities. They are involved in weak nuclear forces and play a role in nuclear fusion and decay. So anytime a nuclear activity is happening, neutrinos are involved. For example, the sun's core is a massive nuclear fusion reaction, so naturally, it produces a lot of neutrinos. Earlier studies suggest that if you hold your thumb up to the sun, approximately 60 billion neutrinos will pass through your thumbnail every second. But neutrinos rarely interact with ordinary matter, despite the billions upon trillions flowing through our bodies every second. Can you imagine throughout your lifetime the total number of neutrinos that will directly interact with the atoms of your body is only about 1? Neutrinos are so ethereal and effervescent that for decades physicists assumed that they were massless particles traveling through space at the speed of light. But after some time, evidence hinted that neutrinos have a small mass. Exactly how much mass is a matter of active scientific research. There are 3 types of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. Each of these neutrinos is involved in different kinds of nuclear processes, and all 3 neutrino types have the strange ability to switch identities as they travel. So even if you observe a neutrino and figure out what type it is, you only know a fraction of what you want to know. And the most high-energy neutrinos are so rare that existing detectors such as IceCube in Antarctica and Kamiokande in Japan have only detected a handful. Scientists need a bigger detector to expand their understanding of these mysterious and theoretically abundant particles. These 2 observatories used water because water is ideal for a neutrino detector. When one of the trillions of passing neutrinos happens to hit a random water molecule, it gives off a brief flash of light. Unfortunately, the entire might of IceCube has only been able to capture a handful of these high-energy neutrinos after a decade of observation. So because of this, scientists need a bigger detector. This is the idea behind the Pacific Ocean Neutrino Experiment, P1, a new plan to turn a massive section of the Pacific Ocean into nature's own neutrino detector. Don't worry, the concept is surprisingly simple. The first step is finding a suitable isolated region of the Pacific. Then construct long strands of photodetectors at least 1 kilometer long. The next step is to sink these strands to the bottom of the ocean, preferably over 1 mile, 2 kilometers, and finally attach floats to the strands so they stand upright in the water, like giant mechanical kelp. Currently, the P1 architecture consists of 7 10-string clusters, with each string hosting 20 optical elements. That's a total of 1,400 photodetectors floating around in the Pacific, covering an area that's miles wide, far more than the area IceCube covers. Once it's up and running, you just need to wait. Neutrinos will hit the ocean water and emit a small glow, and the detectors will trace it. Of course, there are flaws in the design. For one, the strands won't be able to hold still in an ocean as big as the size of the Pacific. The strands will constantly be moving, waving back and forth with the ocean itself. And the world's largest water body isn't full of pure water, with plankton, salt, and a lot of fish excrement floating around. These and other events in the Pacific will change the light patterns between the strands, making it difficult to measure neutrino interactions and forcing scientists to recalibrate the massive machine constantly. As of now, the P1 does not exist, but the research team behind it hopes to build a smaller 2-strand demo as a proof of concept in the next years. If it works, we could be on the verge of a new era of cosmic research, neutron hunting. If you like this video, please consider subscribing and click the notification bell so you do not miss any upcoming videos.